So welcome to another video series on RCC, and in this video we'll be discussing about the column and design of column. So what is column? A column is a member that undergoes large axial compression as well as bending, and the bending is due to the eccentricity of loading, that is the loading is axial load. Let's write the design steps. So the very first is find depth D and width of the column, and if not given, if you are not provided with the depth and width of the column, then we can find it. So there is a formula which we can find in IS 456-2000 page number 71 clause 39.3. PU is equal to 0.47 FCK AC plus 0.67 FY ASC. AC is the area of concrete, ASC is the area of steel, and assuming the value of percentage of steel P%, then PU is equal to 0.47 FCK 100% minus P% by 100% into AG plus 0.67 FY P% by 100% into AG. We get AG is equal to gross area. So gross area is the total area of column, that is B into capital D. Then P percentage is the steel provided, so 100% minus P%. Now assuming square column, B will be equal to D. Then what is B? Then AG is equal to B into D, or B square. B is equal to under root AG, that is gross area, and we will get D also. So B is equal to D. The second step is to calculate the effective length according to the question. As I said, according to the question, or we can say according to the condition of restraining. Okay, either the column is restrained in position and rotation in both ends or not. Effective length is the unsupported length. You can find this in table number 28 in IS 456. Column restrained in position and direction at both ends, then it will deflect in this pattern, and the point from which deflection starts is the effective length. Third step is slenderness ratio. So slenderness ratio is required to check whether the column is short or long. So slenderness ratio lambda is equal to L effective by least lateral dimension. So what is least lateral dimension here? Let us draw a column. It has dimension in y axis and x axis, so whichever is small is taken as least lateral dimension. For generally breadth is taken along y axis and depth is taken along x axis, and breadth is considered as a smaller dimension. For example, if you are provided with 400 into 500, then 400 will be the breadth and 500 will be the depth. If lambda is less or equal to 12, it is short column, and if lambda is greater than 12, it is long column. L effective is equal to 0.65 L for the restrained condition in both direction and rotation. Basically, short column fails by the crushing of concrete and long column fails by crossing and buckling of concrete. Now we have to check for the type of loading, that is either the case or either the column is axially loaded or biaxially loaded or uniaxially loaded. For this we have to find the value of Ex and Ey, which we can find as Ex is equal to L by 500 plus D by 30. Ey is equal to L by 500 plus B by 30. This can be found in clause 25.4 page number 42 of IS 456. That is, all columns shall be designed for minimum eccentricity equal to unsupported length of column by 500 plus lateral dimension by 30, subject to a minimum of 20 mm. When biaxial bending is considered, it is sufficient to ensure that eccentricity exceeds the minimum about one axis at a time. So basically eccentricity less than 20 mm or the moment due to the eccentricity less than 20 mm is neglected. Now we have to check for axial, uniaxial and biaxial case. Now if Ex is less than 0.05 D and Ey is less or equal to 0.05 B, then it is axially loaded case or plan of column, and drawing the axis x and y. Along y axis we said B, and along x axis it is taken as D. Note, Ex is the eccentricity along x-axis and Ey is the eccentricity along y-axis. Also, if Ex is greater than 0.05d or Ey is greater than 0.05b, any of these conditions satisfying, that is, if Ex is greater than 0.05d and Ey will be less or equal to 0.05b, then it will be a uniaxially loaded condition. If eccentricity is more than 0.05d or 0.05b, design moment due to eccentricity has to be considered. In axially loaded case, we had ignored or we had neglected the moment due to eccentricity as described in the code. Now, if Ex is greater than 0.05d and Ey is greater than 0.05b, it is a biaxially loaded case. Now, moment has to be calculated along both axes due to eccentricity. That is, moment along x and y in both direction is considered due to eccentricity along x and y direction. That is MUX and MUY. MUX is equal to PU into EY. PU is the compression load and EY is the eccentricity along y-axis about x-axis. It is the perpendicular distance from the origin. EY is the perpendicular distance for PU along x-axis and MUY is equal to PU into AX. Then from clause 39.6 for biaxial bending, we have MUX by MUX1 to the power alpha n plus MUY1 by MUY, 1 alpha n is less or equal to 1. So this condition has to be satisfied, where MUX and MUY are the design moment along x and y. MUX, 1, MUY, 1 is equal to moment capacity for axial load, PU along x and y, and alpha n is a term that depends upon the ratio of PU and PUZ. And PUZ is equal to pure compressive load, which is equal to 0.45 FCK AC plus 0.7 FY ASC. This can be found in the clause 39.6. Moment capacity MUX, 1 and MUY are determined from the interactive diagram from code SP16. So what is interactive diagram? So interaction diagram is a curve that shows the possible combination of moment and axial load that cause failure to a given cross section. Possible because with increase in the applied moment, the axial load capacity of a section decreases. The diagram has two axes, the Cartesian y-axis representing the normalized axial load, that is PU by FCK AC. AC here is BD, and the x-axis here shows the normalized moment, that is MU x or y, 1 FC divided by FCK BD square, basically AC into S, that is BD square, and this is the common representation. Now next step is reinforcement detailing. There are certain criteria, that is area of steel minimum provided should be 0.8% of the gross area. Area of steel provided maximum should be 6%, 3% and 4% of gross area according to codal provision. Preferred case is 3% and allowed case is 4%. Minimum bar size. For the case of column, minimum bar size, that is 5L, is 12 mm and 4 numbers for rectangular and 6 number of rebar has to be provided for the circular column. So now lateral tie. Lateral tie are the reinforcement provided for the prevention of shear failure. These are also known as shear reinforcement, as it holds the rebar, so shear failure is avoided or is reduced. Diameter of the lateral tie, that is 5T. The diameter of the lateral tie should be greater than that of 1/4 of diameter of longitudinal bar or 6 mm, whichever is greater. That is, if the value of longitudinal bar is 12 mm, then 12/4 is 3 mm. So we will be taking 6 mm because 3 is smaller than 6, so taking the greater value. And pitch. Pitch is the center to center distance for the lateral tie, as you can see here. Pitch should be taken least of 16 phi L, least lateral dimension, or 300 mm, whichever is small. For the diameter case, whichever is greater is taken, and for the pitch, whichever is small. Closer the lateral ties are provided, more resistant to shear failure. And in case of multi-dimension bar, for example, if we are having 12 diameter and 14 diameter bar, then For the case of diameter, that is 1 by 4 pi L, we have to provide the diameter which is greater, that is 14, and for the pitch we have to provide the smaller diameter, that is 12 mm, that is 16 into 12. So generally in field we might not have only 4 rebars, we might get a number of rebars in between the corner bars. So for that extra lateral tie is required or not. So the very first step for determining whether the extra stirrup is required or not, we have to find the spacing between the bars along x-axis and along y-axis. We have to check for the respective axis. So diagram of the reinforcement. So 6 bars we have here, D being the overall dimension, D dash being the effective cover. Now spacing between bar is equal to D minus 2 into D dash, because the effective cover is provided along 2 position along each axis, divided by 2, that is the number of spacing between the bars. In our case there is 2, so we are writing 2. If it exceeds 75 mm, then stirrup is required. Now type of stirrup, we have to determine whether we have to provide closed tie or open tie, for which spacing between corner bars has to be determined, which is equal to D minus 2 into D dash. D is the overall depth and D dash is the effective cover. And if spacing between corner bar is greater than 48 times of the diameter of lateral tie, then closed stirrup is to be provided, and if it is less than 48 times of the diameter of lateral tie, open type of stirrup is provided. So in case of open type stirrup, we can directly provide closed stirrup, because closed stirrup is much more stronger. So this is a closed stirrup and this is a open type stirrup.